Today we will discuss about the operator J and its application and its representation, like graphic representation and different types of representation of this operator and its application to AC circuits. First of all, we will discuss about the operator J and its application to AC circuits. Suppose we have an expression 8 plus 2. This means adding two numbers 8 and 2, 8 plus 2. This indicates that 2 is to be added to 8. Then the plus sign shows that an operation of addition is to be performed on 2. Similarly, in the expression x minus 2, the operation of addition of minus 2 is done, or the operation of subtraction of plus 2 from 8 is to be performed. The sign plus or minus may be considered as marks representing these operations of addition and subtraction. So these operations, operator plus or minus indicates the symbols plus or minus indicates the operations of addition or subtraction that is to be performed in this expression. So next, consider the quadratic equation of the form x square minus 2x plus 10. So the solution of this equation according to minus b plus or minus square root of b square minus 4ac by 2a, the solution will be of this form, and we will get 1 plus or minus square root of 1 minus 9. Each root of the equation consists of both a real and an imaginary part, because this is the real part and this is square root of minus 9. This will converge to an imaginary part. So each root, there are two roots, 1 plus square root of minus 9 and 1 minus square root of minus 9. So there are two roots, and both this root includes both real and imaginary part. The combination of real and imaginary quantity is called a complex quantity. So any quantity which is a combination of this real and imaginary quantity is known as complex quantity. The square root of a negative number is an imaginary quantity. So the square root of imaginary quantity negative quantity can be represented as an imaginary quantity. Square root of minus 9. Here the imaginary part is minus 9. So that can be represented as square root of 9 into minus 1, which will be plus or minus 3 square root of minus 1. Because we can take this 9 from the square root, so that will be plus or minus 3, and this is square root of minus 1. So minus square root of minus 9 can be represented as plus or minus 3 square root of minus 1. The problem of giving a meaning to the square root of any negative number reduces to that of finding a meaning of square root of minus 1. So for convenience, square root of minus 1 is usually written as j. So finding any square root of any negative number, as we are simplifying as finding the square root of minus negative 1. So for convenience, minus 1 is written as j, square root of minus 1. This square root of minus 9 can be represented as plus or minus 3 into j, since square root of minus 1 is now represented as j. Okay. Now 3j is called an imaginary number and is a real multiple, positive or negative, of j. Okay, so minus quantity is represented using this imaginary number. The quantity j, although an imaginary quantity, is used to indicate a real operation, and it's therefore called an operator. So the j is called as an real operator. Okay, any complex quantity can be written in the form a plus jb, where a is the real parts of the complex quantity. A and b are real parts of the quantity, real numbers of the parts. Now, since j is equal to square root of minus 1, j square can be represented as minus 1. J square will be minus 1. Squaring both sides, we will get minus 1. And j cube can be represented as j square into j. So, that is minus 1 into j, which is minus j. So, j cube will be minus j. And again, j4 can be represented as j square into j square, which is minus 1 into minus 1, which is plus 1. So, j raised to 4 is plus 1. And if we are taking 1 by j, we can represent it as j by j square. So, that will be j by minus 1, since j square is minus 1, which is again minus j, and so on. So, any operation or any power of or any form of j can be converted into forms like this by operating it with j square. So, the quantity we already know is j square, which is minus 1. Okay, so this is about the operator j in brief. So now we'll discuss the graphical representation of imaginary quantities, which is known as Argon diagram. So all real numbers can be represented as points on a line, positive to the right of the origin and negative to its left, like this. So any real quantity can be represented on a like this, positive on right and negative on. This is a usual procedure we already know. For representation of imaginary numbers, however, we turn to the interpretation of j as an operator. We can convert an imaginary number into a real number by the use of this operator. So for representing the lines on real numbers on along a line is already know, and for representing in imaginary numbers, we turn to the interpretation of j as an operator. Okay, so for example, 1 into j is equal to minus 1. This plus 1 has been converted into minus 1 by the operator j. So what happened here? Here 1 is multiplied with j square. Okay, and it is converted into minus 1. J square is minus 1, so 1 into minus 1, which will give you minus 1. So here the 1 is operated with the operator j square and it is converted into minus 1. So the result is minus 1. So plus 1 has converted into minus 1 by the operator j. The figure shows this figure, not this one. The figure shows the plus 1 can be converted into minus 1 by, so this is plus 1 and this is minus 1. Here the operator with j on 1 is the result of converting 1 to minus 1. So here in this line, the plus 1 can be converted into minus 1 by an operator, by an operation of 180 degree rotation. So 1 is turning into minus 1 when we rotate it through 180 degree. Okay, thus the operation of multiplying plus 1 by j square is equivalent to turning the line 0, 1. 0, 1 means this line through 180 degree. So the operation j square means turning this line through 180 degree. Okay, so this is what is meant by the operation j square, a 180 degree rotation. Multiplying by j square is the same as multiplying by j twice. Hence, multiplying by j only once is equivalent to turning it through 90 degree. Since J square operation means rotating a line through rotating or an operation of 180-degree rotation, since J square can be represented as multiplying J twice, so J represents a rotation of sorry rotation through 90-degree. This turning may be brought about either clockwise or anti-clockwise, and the direction of rotation can be clockwise or anti-clockwise. We will explain how it happens. Anti-clockwise rotation through 90-degree is taken as the operation of multiplying a number by plus j. Clockwise rotation through 90-degree as the operation of multiplying a number by minus j and vice versa. So this is about the direction. So anti-clockwise rotation through 90-degree is taken as operation of multiplying a number by plus j and multiplying by minus j represents clockwise rotation. Sorry. Now, square root of minus 9 has two roots, plus 3j and minus 3j. The square root of minus 9 may be represented graphically by turning the line 0, 3 through 90-degree anti-clockwise or plus 3j and clockwise for minus 3j. That is, so we have already said that the clockwise rotation is represented by plus j operation, minus j operation, and anti-clockwise 90-degree rotation is represented by plus j operator. So here in this example we have got square root of minus 9, which is plus or minus 3j. So plus or minus 3j can be interpreted as plus 3j as anti-clockwise 90-degree rotation and minus 3j as clockwise 90-degree rotation. So this is what is meant by plus 3j and minus 3j. Okay. Since 1 by j is equal to minus j, we have already seen that the operation of dividing by j may be interpreted as clockwise rotation of 90 degrees. Since this is minus j represents a minus 90-degree rotation. So 1 by j is represented as a minus 90-degree, means a clockwise rotation through 90-degree. Hence, when j operates on a quantity, it rotates through 90 degrees. So in simply the operator j means a rotation through 90-degree. Okay, and the minus sign, minus or plus sign is interpreted as the rotation through clockwise or anti-clockwise direction. So operation j operates on a quantity means it rotates through an angle 90 degree. Thus we find all imaginary numbers. Find that all imaginary numbers may be represented graphically by drawing a line through 0, that is the origin, at right angles to the line on which real numbers are represented, like what is shown in figure here. So in a quantity, all imaginary number may be represented like this. So we are drawing axis like this. This is real axis and this is imaginary axis. Here we have represented the imaginary quantity j, minus 2j, minus 3j, etc. here, plus imaginary quantities. So a vector. So if we are considering a vector or a point, an imaginary quantity in this we are representing an imaginary quantity in this diagram. We can represent it like this. For example, 4 plus 2j. 4 plus 2j means 4 on real axis and 2j on positive imaginary axis. So 4 2j. So this is the point and this is the vector representing 4 plus 2j and which is represented as z. Okay. So in the graphical representation, it can be represented like this. This gives rise to two axes at right angles. This we are talking about this graph, two right angles to each other. A diagram on which both real and imaginary numbers are represented is called Argon diagram. Such a graph is known as Argon diagram, where we can represent both real and imaginary axes. So such diagrams are known as Argon diagram. For example, 4 plus 2j is represented here like I explained. So OA is the vector representing 4 plus 2j. It may be noted that the part of any complex number which does not involve j lies in the direction of x-axis and is called the reference or phase component. So the part which has no j component is lie on the x-axis and is known as reference or phase point, and that part of the expression which contains the factor j is called the quadrature or called the quadrature component. So the number has two parts, both real and imaginary parts. So those part which does not have j part is known as reference or phase component, and the part which has j factor is known as quadrature component. The magnitude, that is the absolute value of complex number, is given by the square root of the sum of squares of the reference component and quadrature component. That is, if z is equal to x plus iy is the complex quantity, this is the reference component and this is the quadrature component, and the magnitude of z can be represented as square root of sum of this reference component and quadrature component. That's what we said. In dealing with AC circuits, we have made use of vector diagram method. It is, however, possible to express vector quantities in such a way that one might deal with the quantities as if they were simple algebraic relations. So in AC circuits, we are applying this Argon diagram method for representing the currents or charges, etc. You have already seen when we were dealing with the Lcr circuits, etc., AC circuits. Okay. Now, vector and the j operator. We'll discuss different types of representation of vector, means the j operator. All vector quantities, example force, alternating current, etc., can be represented in magnitude and direction by a straight line. This is a usual procedure of representing a vector. Okay, also a vector can be resolved into two components at right angles to each other. That is also, we know, a vector can be usually resolved into two perpendicular components. There are 4 forms in which a vector can be represented mathematically, making use of the operator G. So, a vector can be represented mathematically in 4 forms, 4 types, 4 different forms. Okay, making use of the operator J. So, we have already know what is the operator J, and a vector can be represented in different 4 forms using the operator J. We will look at that. We shall symbolize complex quantities by boldface, Roman type, or with a dash above them. You know how a vector can be represented while writing. That's what we are describing here. Now, the first form, the symbolic or rectangular form of vector representation. Symbolic, or we we said that there are four forms of representation of a vector using the J operator. This is the first form, symbolic or rectangular form of vector representation. Suppose the vector R is included to the reference direction OP at an angle phi. So here I have shown here, this is the reference vector R. This is the vector R is is inclined to the reference direction P. So this is the reference direction OP, and the vector R is inclined to OP with an angle phi. The vertical component B is rotated 90 degree in a counterclockwise direction with respect to OP. So this is the vertical component which is rotated through 90 degree counterclockwise direction. This is counterclockwise direction. So from the reference point, it is rotated through 90 degree counterclockwise direction in order to get this direction or this vertical component. With this, denote this component vector along PQ by B as J into B, since J represents the 90 degree operation counterclockwise. Okay. The component A along OP is denoted by A. So this is this vector has no change. So this is along the reference direction. So it can be represented simply by A. So the resultant R vector can be represented as the combination of A plus JB. That is, the component B part is rotated 90 degree counterclockwise from the reference line. So this is represented as JB, and this is along the reference direction. So the resultant will be sum of these two components. So the resultant vector R is can be represented as a combination of these two components, A plus JB. The magnitude of the resultant, however, can be represented as square root of this sum of the components A square plus B square, and its phase with respect to OP is given by tan phi is equal to B by A, which we can obtain from the components by sine and cosine components. So if we are taking the sine and cosine component from this, we will get the equation of tan phi as B by A. Okay. So in the figure B, Z is equal to X plus JY, and this is the figure we have represented like a diagram like this, and Z is representing vector Z can be represented, complex quantity can be represented as X plus JY, and its magnitude is represented by square root of X square plus Y square, sum of the square of its reference component and quadrature component. In the equation of R, A and B are real numbers. Here A and B are real numbers, and the vector R is the sum of the vectors A and B. The presence of J is thus indicates the vector B has been rotated through 90 degree in the anti-clockwise direction, or is said to lead the component A by 90 degree. So here we have seen how the vector R is represented as a combination of A and B, which is A plus JB. So which means B has rotated through 90 degree counterclockwise. Counterclockwise means in the positive direction. So clockwise. We can say that the component B is lead A by 90 degrees. Since A is along the reference direction, only B is rotating counterclockwise through 90 degree. So we can say the component B is lead A by 90 degree. The vector R written in a complex form. So this representation is known as a complex representation. In electrical engineering, A is called in phase or active and B is called the quadrature or reactive component. This the operate, that is we are using this as a reference component and quadrature component. In electrical engineering, they are using active or reactive components. That's all. This the operator plus J. This the operator plus J. Although the imaginary square root of -1 is defined as 1 whose effect is to be rotates its operand through an angle pi by 2 in the anti-clockwise direction without altering the magnitude of the operand. This is already explained. We are explained this in another terms. That's all. The physical significance of the presence of plus indicates a phase advance of 90 degree and the presence of minus j a phase lag of minus 90 degree. That is the counterclockwise rotation. Plus j we represent as a counterclockwise rotation, which means a phase advance of 90 degree, and minus j operation, which is clockwise rotation or minus 90 degree rotation, which is a phase lag of 90 degree. There is no minus sign, means because we are already saying that this is phase lag, so phase lag of 90 degree. Okay, this in dealing with vector quantities, the terms such as JB does have a physical significance though. So when we are dealing with vector quantity, this J into B or the operator J into any quantity in that vector does have a physical significance. Okay, it would thus be realized that just on symbols, multiplication, addition, square root of, integration, d by dx, del are used with numbers or quantities for indicating certain operation to be performed on them. Similarly, plus j is used to indicate counterclockwise and minus j clockwise rotation of a vector. So j is an operator and its operation is a clockwise or anti-clockwise direction according to its sign. That's what it simply mean. The presence of j square in front of a vector, that is j square into b, that is j square is appearing in front of the quantity b or a vector, which is equal to, the result is minus b, since j square is equal to -1, means that it is 180 degree ahead of a or 90 degree ahead of b. So b is converted into minus b, so this is 90 degree ahead of b or 180 degree ahead of a, and jb is equal to minus jb, means that is equal to minus jb means that it is 270 degree ahead of a or 180 degree ahead of b, and so on. So also, instead of speaking of direction of r, we speak of the phase of r, the phase being given by angle phi. So instead of talking in terms of the rotation through angle, we are in speaking of the direction, we are speaking in terms of this phase. That's all. Now the second form is the trigonometrical form of vector representation. So what is trigonometrical form of representation? If theta is the phase angle, between the vectors, then we can write the components x as e cos theta. This is the phase angle. So we can represent the component x component as e cos theta and y component as e sin theta. So the vector can be represented as e cos theta plus j into e sin theta, because the y component has rotated through 90 degree anti-clockwise, which can be represented by the operator j. So the vector quantity can be represented as the combination of these two real part using the J operator like this. So this is another form of vector representation using the operator J, and it is known as trigonometrical form of vector representation. And the third form is exponential form. So exponential form means the just above equation can be represented as E is equal to E into E raised to J theta. For E raised to J theta, we can expand this using the Taylor series. The expansion of E raised to theta will be I1 plus theta square by 2 factorial plus etc. So here instead of theta, J theta appears. So the expansion will be like this. So the resultant is 1 plus J theta, J square is minus, so minus theta square into 2 factorial is 1 into 2 plus etc. Similarly, we are expressing E raised to minus J theta as series expansion. So we will get. Now if we add these two and divide by 2, we will get the right side as like this. Sometimes we'll cancel each other and the remaining term will be like this. So this is nothing but the series expansion of cos theta. Similarly, if we are subtracting those two equations and divide by 2, we will get J sin theta. You can write it on a paper and check whether this result emerges out. It will emerges out. You have to check it. Okay. So we'll get cos theta and sin theta series in this form. Therefore, e raised to j theta can be represented as cos theta plus j sin theta. And so if we are adding these two equations, we will get cos theta plus j sin theta on right side and e raised to j theta on left side. Similarly, if we are subtracting this equation, we will get cos theta minus j sin theta on right side and e raised to minus j theta on left side. Therefore, the exponential equation can be written as e cos theta plus j sin theta as e raised to j theta. Since this is of the form, this equation is in the form of this equation, so this can be simply represented as e raised to j theta. Cos theta plus j sin theta is nothing but, since e can be taken outside as common, so the remaining term is cos theta plus j sin theta, which is nothing but e raised to j theta. So this vector can be represented as e into e raised to j theta. So this is the exponential form of representation of vector using the operator j. Now the fourth form is polar form. Fourth and last form of representation, polar form. The expression e into cos theta plus j sin theta is sometimes written as e and this symbol theta, where e is the magnitude of the vector and theta is the inclination. So e is inclined with theta in the anti-clockwise direction with the x-axis. For angles in clockwise direction, it is written as e inclined with minus theta. So thus e angled plus or minus theta is shorthand for e raised to e to the power plus or minus j theta. So this is just another form of representation, and here we are representing this operator as the inclination with the phase angle. That's all. Okay. In case of an AC circuit containing ohmic resistance R and reactance X, the impedance Z is represented as a vector quantity which is given by Z is equal to R plus Jx. This is the form of impedance representing a circuit containing purely ohmic resistance and an inductive reactance. Okay, so and its magnitude or modulus value can be obtained as square root of R square plus L square omega square, and Z as so Z can be also represented as Z into e raised to j theta using this form, exponential form. Okay. So which is a complex vector impedance where tan theta will be obtained by the ratio of this inductive reactance and the ohmic reactance. Similarly, the complex vector impedance may for an Lcr circuit be written as, so this you have already seen while dealing with Lcr series AC circuit. So Z can be represented as Z into cos phi plus j sin phi, which can be represented as Z into e raised to j phi in the polar form, in the exponential form. So this is r plus j into omega L minus 1 by omega C. This is the ohmic resistance. I think this is the part for inductance and capacitance part. So the combination of inductive reactance included. So sin phi we will obtain by from the circuit as omega L minus 1 by omega C. These terms are already explained the series Lcr circuit. So we need not to explain it in detail here again. So sin phi is omega L minus 1 by omega C by Z and cos phi is R by Z. So tan phi we will obtain like this, the ratio of these two. Now if E is equal to E0 j omega t, then I is equal to E by Z, which is equal to E0 raised to j omega t by Z e raised to j phi. Okay. Now, since E is equal to E0 j omega t, okay, so we are representing this like this, and Z have a complex form of cos phi plus j sin phi, so we are representing E and Z like this. Now, e raised to j is common in both, so we can combine these two terms together and can write like this. But E0 by Z is nothing but I, so this is I into e to the power j omega t minus phi. The real part of R of this vector impedance is often called the resistive or in phase component, and the imaginary part is called the reactive or quadrature component. So real part is a resistive component and imaginary part is this. Real part is resistive component and imaginary part is reactive component in a circuit containing both ohmic resistance and reactance. Okay, so this is the application in AC circuit. In the polar form application. Okay, now we will discuss in general the applications of J operator to AC circuits. We have already seen that alternating quantities can be represented by vectors, and as complex numbers are equivalent to vectors, they may also be used to show the relation between RMS values and phase of alternating quantities. So any alternating quantities represented by vectors, and the vectors can be represented in form of complex numbers, so which will give you the relation between RMS values and phase of alternating quantities. The generalized Kirchhoff's laws for AC circuits in the complex form are, so you know what are Kirchhoff's laws for AC circuits, and in the complex form they can be stated as, the first one is the algebraic sum of all the complex currents meeting at a point is 0. This is the first law. And the algebraic sum of all the Zi terms around any closed path, Zi means this is the impedance path, equal to the algebraic sum of the complex applied EMF in the given path. Okay, this is Z into I, this is impedance, this is current, so Z into I will give you the EMF. So the algebraic sum of all the Zi terms around a closed path equals the algebraic sum of the complex applied EMF in the given path. So these are about two laws, which is stating about the currents, which is about the EMF. Okay. Now we will consider only the series circuit here, application of J operator to the series circuits. Now the series circuits by using the operator J, which is square root of minus 1. So the first case is for an AC circuit containing ohmic resistance only. Okay, for an AC circuit containing only ohmic resistance, the vector diagram consists of two lines of magnitudes E and I in the same direction. On the Argon diagram, they are represented by two distances along the positive axis of real numbers. So, in the pure ohmic resistance circuit, there is no imaginary part appears. So, the quantity can be represented as real numbers. So, along the positive axis of real numbers in the Argon diagram. And for an AC circuit containing only inductance, applied EMF leads the current by 90 degrees. So in the purely inductive circuit, the applied EMF always leads the current by 90 degree. So and are related to each other by the relation E is equal to omega L into I. So in the Argon diagram, I is represented along the real positive axis while E represented along the positive imaginary axis. So as I along positive real axis and E along the positive imaginary axis, which means E leads I by 90 degree. Positive imaginary axis of magnitude omega into L. E is therefore fully represented by the equation. So E can be represented as J omega L I0. So since it is leading I by 90 degree, we can represent this equation like this. So that is the representation for purely inductive circuit. Now the third one is for a circuit containing R and L in series, ohmic resistance and inductance in series. So the resultant EMF can be represented by this equation, the combination of the EMF across the resistance and ohmic resistance and inductance. So this is the I0 is common here, can be taken outside. So the remaining part is a combination of real part or reference part and quadrature part. And we know from the Lcr series circuit, the phase tan phi phase is represented by this expression tan phi as omega L by R. Now complex vector impedance can be represented as the combination of this purely ohmic resistance plus inductive reactance. So this can be represented as Z into e raised to I phi, which is Z into cos phi plus j sin phi. Now the magnitude of this set quantity from this equation we will get as R square plus omega square L square root of. The real part is called the resistance. This is real part. This is resistance and or in phase component, and the imaginary part is the reactive or quadrature component. Now the circuit containing purely capacitor only series circuit. So here E0 is minus J0 by omega C, which means E lags behind I by 90 degree. A minus J operator appearing here, which means E lags I by 90 degree. Hence it is represented by the equation like this. So minus J can be represented as 1 by J, which is, so this will be of the form I0 by J into omega C. The reactance is 1 by omega C. Okay. So these are all just representation how we are applying this to the series circuit. Okay, the theory we already know, and we are applying this operator to these circuits. That's all. For an RC series circuit, the E0 is of the form this, and so I0 can be taken outside. So this will be of the form, and the impedance is represented by this equation, and the magnitude of the Z is represented by this equation, and the phase angle will be of the form 1 by omega c into r. Okay, now for Lcr series circuit, again we know the equation of EMF as the form like this, where R plus Jx is set the impedance of the circuit, complex vector impedance, and X is here, since it is a series Lcr circuit which contains reactance offered by the inductor and the capacitor. So X will be a combination of this inductance offered by this inductor and the capacitor. So we can represent R as J into R plus J into these two. Now this is of the, so we are taking this J inside the bracket. There we are expanding the bracket, so J omega L plus minus J by omega c, which can be represented as 1 by J omega c. Also R plus Jx is such that its length on the Argon diagram is square root of R square plus X square. That is the magnitude of this vector. The magnitude of the impedance is given by we will obtain from this expression as square root of R square plus omega L minus omega 1 by omega c all square. Therefore tan phi is omega L minus 1 by omega c r. Three cases arise here. One is because in the impedance term two terms appears, and the second term is a combination of these two. So according to the nature of these quantities, three cases arises. If omega L greater than 1 by omega c, EMF leads I, and if omega L less than 1 by omega c, EMF lags behind I by phi, where phi is represented by this equation, which will be tan inverse of this quantity. And when omega L is equal to 1 by omega c, phi is equal to 0, E and I are in phase, which means these two are equal, means E and I are in phase. This is the case of resonance. In this case, omega is equal to 1 by square root of Lc, and resonant frequency F is equal to 1 by 2 pi into root Lc. So this is how we are applying the operator J to the AC circuits. Okay, you are already familiar with the AC circuits, and this is how the operator J is applied to this AC circuits and the representation of the operator J is vector. Okay.